Oh, does that have a...
Mute.
Hola, buenas tardes, bienvenidos todos. Welcome everybody. It is a pleasure to introduce Professor Terence Tao from University of California, Los Angeles, who is going to talk to us about the Erdos discrepancy problem.
Thank you. Thank you very much. Thank you very much. This has been a great trip to Chile so far. So much hospitality. So I'll be talking about some work I did about 2 years ago, actually 3 years now, solving an old question of Erdos in discrepancy theory. So before I talk about my problem, let me tell you a little bit about discrepancy theory, which is mathematics of trying to make mathematical distributions as uniform as possible. So to motivate, just to give an example, in computer science, when you want to compute things, many algorithms used in computer science rely at some point on random numbers. They use random number generators to create some random set of points or random set of numbers to do things. So here's an easy example. Suppose you have some region in space, maybe a subset of a square. So imagine this is part of a square, and you want to find its area. So you could maybe try to divide this region up into tiny squares and count up the area of each square, but sometimes that's hard to do. And maybe you don't want an exact measurement of the area, but just an approximation. So one fast way to estimate the area of an object like this is called Monte Carlo integration. What you can do, so here's the same region inside the unit square. You could generate a large number of random points in the square, maybe say 100 random points, these red points here. And you just see how many of these points lie inside your region. And the proportion of points that lie inside the region would be an approximation to the area of the region. That comes from something called the law of large numbers in probability. So maybe if, say, 40 of the 100 points here lie inside this region, then maybe this region should have area about 0.4. Okay, so that's the Monte Carlo method for estimating area. You can also use it to estimate integrals, and it works in many higher dimensions. So it's a reasonably good method, and we know that if you pick enough points, if you pick millions and millions of points, it will eventually be a good approximation. But if you only pick a few points, like 100, it's not that great of a method, because these points are not very uniform. For example, you see here there's a big empty region where not many of the random points were lying in. And so a lot of the area of this region has somehow been missed by this Monte Carlo method. Conversely, maybe there's a region here where there's too many points. The number of points in this region is maybe larger than the average, and maybe you're counting this region a bit too much. So it's the random points are not as uniformly distributed as you might like for this method. And so when you actually do a Monte Carlo method to compute integrals, sometimes you don't use a random set of points. Random is not always the best method. And so sometimes it would be better to use a grid, if you use an equally spaced Cartesian grid, that also has some problems, because maybe if your set is just a little bit off above one of the grid lines, you also might be imbalanced. But there are other sets of points which are better to use. And the topic of discrepancy theory is the topic of trying to whether you can design sets of points or other configurations of numbers or whatever, which are somehow better distributed than random sets that don't fluctuate as much, have less discrepancy. So random sets, they can cluster. There can be some regions of space where there's too many, or some regions where there's too few, and you want to somehow, and that's a lot of discrepancy, and you want to somehow arrange sets of things better than randomly to remove these random clusters. And that's in general what discrepancy theory is about. How well can you make things, how well distributed can you make sets like this? Okay, so that's not what I'm talking about. That's just sort of a general motivation for the subject as a whole. So I won't be doing this two-dimensional area counting anymore. The Erdős discrepancy problem is a question about one-dimensional discrepancy theory. So in some ways it's simpler, but you can't draw pictures as well. So it's a more combinatorial problem. So now we have a one-dimensional sequence of just plus and minus ones. Okay, so this is called a sign sequence or sign pattern. Okay, so here's a sign pattern, plus 1, minus 1, minus 1, plus 1. It's just a sequence of plus ones and minus ones. Now, there are many such sequences, and you can generate them randomly. If you want to generate a sequence like this, you could flip coins, heads plus 1, tails minus 1, flip a lot of coins, you get random sequences. And the laws of probability, the law of large numbers, tells you that if you flip a lot of coins, you would expect half of them to be heads and half of them to be tails. So if you pick a random sequence, about half of, like if you pick, say, 100 signs at random, about 50 of them should be plus 1 and about 50 should be minus 1. So when you add them all together, you should actually get something close to 0. Okay. If you add together 100 signs, you could get a number anywhere between minus 100 and plus 100, but if you choose them randomly, there will be a lot of cancellation, and you would expect a much smaller sum. So these are the sums we will call discrepancies. And so random sequences have reasonably small discrepancies because of a lot of cancellation. But in discrepancy theory, you would ask how small, really what is the smallest discrepancy we can make, and our random sequence is the best we can do. Okay, now to answer this question, you have to be a bit more precise what you mean by discrepancy. So here is an easy example of this. Suppose you have a sequence of signs, let's say 1 million signs, okay, plus and minus 1. And suppose you want to make all the partial sums small. So you want F1 to be small, F1 plus F2 to be small, F1 plus F2 plus F3 to be small. So you want for every partial sum of the sequence, you want them all to be small. And the question is, what is the smallest you can make all these sums? Can you find a sequence which has low discrepancy on all these partial sums at the same time? So mathematically, you want to make this expression here as small as possible. You look at all the partial sums from 1 to m, and m can be anything from 1 to n, and you want to make all of these as small as possible. So you're minimizing the sup or max of this expression. Now, if you choose this randomly, okay, so of course, you can make it big. If they're all plus 1, plus 1, plus 1, plus 1, this would be of size n. That's fairly big. If you choose the signs randomly, then there are tools from probability, such as something called the Chernoff inequality from probability, and it will tell you that this sum, this expression here would usually be of size about root n. So if you have 1 million signs at random, the maximum discrepancy that you would see should typically be about 1,000. Okay. But that's not the best you can do. You can do much better here. And actually, there's a very simple sequence with very, very low discrepancy. Just take the alternating sequence, plus 1, minus 1, plus 1, minus 1. Okay, that's not random. It's actually much better than random. If you look at the partial sums, 1 minus 1 is 0, 1 minus 1 plus 1 is 1 again. The partial sums are just 1 and 0, 1 and 0, 1 and 0. Okay, so the discrepancy of this sequence is just 1. And that's the best you can do. You can't have a sequence of discrepancy less than 1, because even the very first element, the sum has to be of size 1. You can't make that smaller than 1. So in this case, the random is not the best. The best sequence is just the alternating sequence. This is what we call a sub-random sequence, a sequence which is better behaved than random sequences. And so sometimes the random method is not the best. So just to give a physical model for what I just said, when you row a boat, they have these long boats, and you have these people rowing the boat, and each person either rows it on the left or on the right. And usually when you row, you alternate left, right, left, right, left, right, just like this sequence here. And that's because that sequence is low discrepancy. If you did it randomly, right, right, left, left, right, it would be less stable because the discrepancy is higher. Okay. Okay, so that was a simple question with a simple answer. Now let's take a more complicated question with a slightly more complicated answer. So again, take a long sign pattern, let's say 1 million signs plus minus 1. And now we want low discrepancy not just for the partial sums, so we still want the partial sums to be small, but we also want to sum over every arithmetic progression. And we also want this pattern to be balanced, not just from 1 to 2, 1 to 3, 1 to 4, but along every arithmetic progression. So for example, f of 3 plus f of 5 plus f of 7, we also want to be small. F of 10 plus f of 20 plus f of 30 plus f of 40, we want to be small. So we take all the arithmetic progressions in your sequence and you ask, can you make all those sums small at the same time? So you want your pattern to be balanced on every one of these progressions. Okay? So again, if you pick the signs randomly, you just flip coins, you will find that once again, this larger expression here, where you take more and more sums, it's still about size square root of n. There might be a log factor, but it's essentially square root of n. Okay, but can you do better than this? Okay, so previously we had the sequence plus 1, minus 1, plus 1, minus 1, and that was a very good sequence. Now that's a very bad sequence, because if you take that sequence and you look at just, say, the even numbers, 2, 4, 6, 8, you get minus 1, minus 1, minus 1, minus 1. Now there's a very large discrepancy. So that's not a good sequence to, that's not a low discrepancy sequence for this problem. So can you do better than random? There's a limit to how much better you can do. So in the previous problem, you could get the discrepancy just as low as 1. But that's not possible for this problem because there's a nice theorem, a classical theorem of van der Waarden in 1927. He proved one of the earliest results in a field of combinatorics, which is called Ramsey theory. And what he proved is the following. So if you take all the natural numbers, 1, 2, 3, 4, 5, and you color them into 2 colors, okay? So red and blue, right? Colors of Chile. Then one of the 2 colors, or you can take 3 colors or 4, okay? But if you say color into two colors, then one of the 2 colors will contain arithmetic progressions of any length. So, for example, as it turns out, even if you just color the numbers from 1 to 9 into red or blue, then no matter how you color, which one is red, which one is blue, one of the 2 colors will contain a progression of length 3. So, for example, here's a coloring of the numbers from 1 to 9, and the number 3, 6, and 9, that's a progression that's all red. So the red numbers here contain a progression of length 3. If you change the color here of 9 from red to blue, then you no longer have a red progression of length 3, but suddenly you have a blue progression of length 3. 1, 5, and 9 becomes blue. And you can check no matter how you try to turn the colors back and forth, blue and red, no matter what you do, you will create somewhere either a blue progression or a red progression of length 3. So that's van der Waarden's theorem. It's a very useful theorem in combinatorics. And you can apply it here, because a sign pattern, plus minus 1s, you can think of as a coloring of the natural numbers into 2 colors. You can think of plus 1 as red and minus 1 as blue. And so van der Waarden's theorem says that if you have a long enough sign pattern, you will either find a very long arithmetic progression of plus 1s or an arithmetic progression of minus 1s. And in either case, you will get a very large discrepancy. So the discrepancy will actually grow. As your sign pattern increases, the discrepancy must grow. Now, in analysis, which is the field of mathematics that I do, that I come from, once you know that something grows, the next question is how fast does it grow? As a function of n, that's the length of the sequence. Okay, so random sequences, the discrepancy grows like square root of n. We now know that for other sequences, the discrepancy must also grow. And actually, it was worked out by Roth, who was also actually a Fields medalist, in 1964. He showed that this discrepancy, if you look at every single arithmetic progression, the discrepancy must grow at least as fast as about n to the 1/4. So not quite n to the 1/2, but n to the 1/4, which is sort of halfway in some sense between bounded and square root of n. Actually, he proved constant times n to the 1/4, but essentially n to the 1/4. And then a little bit later, in '96, Matuszek and Spencer showed that, in fact, this is actually the best bound, that you can actually find sequences whose discrepancy does grow like n to the 1/4, maybe times a different constant. So they're not random sequences, they are sub-random, because random would give you n to the 1/2, but you can do n to the 1/4. Okay. So that solves that problem there. Okay, so the question that Erdős asked, so Erdős is famous for asking a lot of questions, actually, thousands and thousands of questions. But one of the questions he asked is a question which is somehow halfway between the easy problem that I started, where you only look at partial sums, and this other problem where you look at arithmetic progressions. This is a problem halfway in between, where you restrict attention to a special type of arithmetic progression, what are called homogeneous arithmetic progressions. So a homogeneous arithmetic progression is a progression whose spacing, the gap between the progressions, is the same as the starting point. So A, 2A, 3A, 4A, that's a homogeneous progression. So 10, 20, 30, 40 is a homogeneous progression because the spacing 10 is the same as where you start, is the starting point 10. But 11, 21, 31, 41, that's an arithmetic progression, but it's not a homogeneous arithmetic progression because the spacing is 10, but where you start is 11. Okay. So you only look at homogeneous progressions, and you only ask for your sequence to be low discrepancy, to have small sums on homogeneous progressions. You don't ask it to be bounded on every arithmetic progression. Okay, so you include partial sums. Partial sums would be a special case of homogeneous progression. So F1 plus F2 plus F3 is one of the things you want small. But you also want F10 plus F20 plus F30 to be small, or F2 plus F4 plus F6 plus F8 to be small. Okay, and Erdős asked, okay, if this is your notion of discrepancy, can you make arbitrarily long sequences, maybe infinite sequences of signs with bounded discrepancy? Can you keep the discrepancy bounded not just for partial sums, but also for these homogeneous progressions? Now, he had a reason for asking this question. I'll get to it later. He was motivated by some questions in number theory. So Erdős is famous for asking thousands of questions, but each of his questions, they weren't random questions. He always had a reason for asking these questions. All right, so so this question is somewhat in between the previous two questions. Another way of saying it is that, posing the question is that given any threshold C, like say 5, if you take a long enough sequence, if you pick enough elements, like 1 million elements, 1 trillion elements, does it have to be the case that this discrepancy here has to exceed your constant C, has to exceed 5? Okay, so does the discrepancy have to eventually be bigger than 3, bigger than 5, bigger than 10? Okay? So if you phrase the question this way, then you can look at special cases. You can look at C equals 1, C equals 2. You can start understanding the problem by examples. Okay. So for instance, the easiest case is C equals 1. Okay. If you have a sequence, when is it the case that a discrepancy of a sequence has to be at least 1? That's very easy. The moment you have even one term in your sequence, the first n equals 1, the discrepancy has to be at least 1 because you f of 1. You just that's a progression. If you sum that, that has to be size 1. Okay, so the discrepancy has to be at least 1 as soon as you have one element. Okay, of course, if you have 0 elements, discrepancy is 0. Okay, that was easy. What about 2? So when must the discrepancy be as big as 2? So this is already a little bit tricky. So here's a sequence of 11 signs, plus 1, minus 1, so forth. And it turns out this sequence has discrepancy 1. So like if you take, for example, f of 3 plus f of 6 plus minus 1 plus 1, that's 0. Okay. F of 3 plus f of 6 plus f of 9 is minus 1. If you look at every homogeneous progression in this, I'm not going to do all of them, but you can check that all the sums will either be minus 1, 0, or plus 1. You'll never get 2 or minus 2 or anything bigger than that. So the discrepancy is just 1. Okay, so you can have a moderately long sequence where the discrepancy never gets bigger than 1. But it turns out that that's it. Right? Once you get to 12, when you have 12 signs, you must have discrepancy 2 at least. So let me see if I can actually prove this. I was going to use the board, but this is too tiny. So this is something I've never done before. I'm going to use this software on this computer. I don't know if this will work very well, but let's see. Okay. So we're going to claim that any length 12 sequence. Does that work? Can you read that? Okay. Has discrepancy at least 2. Okay. So the way you prove this is by contradiction. Okay. So assume not. Okay. So suppose you have a sequence of discrepancy 1. So suppose you have a discrepancy 1 sequence. F of length 12. Okay, so what we're going to do is we're going to make a little table here. Okay, is that readable mostly? Okay. And we're going to try to understand what F is. And this would be kind of like solving a Sudoku puzzle. I don't know if Sudoku is popular in Chile, but well, anyway. So we have a sign pattern of plus and minus 1s. So f of 1 will either be plus 1 or minus 1. And actually, without loss of generality, we can assume that the sequence starts with plus 1. Because if it starts with minus 1, you can flip the sequence. You replace every element with its opposite sign, and it will still have the same discrepancy. So let's say that the first element is plus 1. Okay, now we play this sort of Sudoku like reasoning. Okay, so if the first element is plus 1 and the discrepancy is 1, then the next element, f of 2, must be minus 1. Because if you have plus 1, then that would add up to 2, and that's not allowed. So f of 2 has to be minus 1. Okay? Now, f of 3 we don't know yet, because either plus 1 or minus 1 won't give you a discrepancy of 2. But we can skip ahead to 4. Okay? 2 and 4 is a homogeneous progression. And because f of 2 is minus 1, f of 4 has to be plus 1. Because if it was minus 1, then minus 1 would give you minus 2, and that's not allowed. Okay? Now, once you know f of 4, now we can go back and fill out f of 3. So, those of you who've done Sudoku, maybe you can start seeing the similarities here. Okay? F of 3 has to be minus 1. Because if it was plus 1, plus 1, minus 1, plus 1, plus 1 would be 2. And that's not allowed. So this has to be minus 1. Okay, let's see. 3 and 6. If 3 is minus 1, 6 has to be plus 1. 4 and 8. If 4 is plus 1, 8 has to be minus 1. What else? Okay, 5. 5 has to be minus 1, because otherwise plus 1, minus 1, minus 1, plus 1, plus 1, plus 1, if you work it out as 2, that's not allowed. 5 has to be minus 1, which makes 10 plus 1. If you look at 5 and 10, let's see, what else I want to do? 6 is plus 1, so 12 will be minus 1. What else I want to do? Okay, 7 turns out has to be plus 1. If you add up all these sums, you have to cancel this minus 1. So this actually has to be plus 1. Otherwise, the first 8 elements will sum to minus 2. Similarly, f of 9 has to be minus 1. If it was plus 1, this would all add up to plus 2. You can check. Okay, but now actually I think I can stop. I don't need to keep going, because if you look at this progression, 3, 6, 9, and 12, that adds up to minus 2. And so now we have a discrepancy of length 2. Okay? So that's a proof that once you get to length 12, the discrepancy has to be at least 2. Okay? And that wasn't too hard. Okay, not many proofs you can give in 2 minutes, but there's one. Okay, so it's an example of what computer scientists call a two-stat problem, and a two-satisfiability problem, which is relatively easy to solve. Okay. Okay. All right, so that's 2. So now you can look at 3. So you can ask, if you make the sequence longer, we now know that discrepancy has to be at least 2. When does the discrepancy have to become 3? So it turns out it takes a while. So 2 computer scientists, Konev and Lisitsa, they did a computer search, and they managed to discover a sequence of length 1,160. So there's a sign pattern of 1,160 signs in length, where the discrepancy never got bigger than 2. Okay, so I just showed you that once you get 12 elements, the discrepancy has to reach 2, but it can stay there for a long, long time. The discrepancy can stay at 2 until 1160 steps. Okay, so that's sort of surprising, but what's really impressive, what they did, is that they showed that this was the best possible. That if you go to 1161, any sign sequence of length 1161, the discrepancy has to become 3 or higher. Now that, you have to, it takes a bit of computer science to appreciate how hard that is to show, because how many sign patterns are there of length 1161? That's 2 to the 1161. That's a huge number. That's more than the number of atoms in the universe. Okay, so they didn't check every case. They solved what's called a 3-sat problem, which is a problem in computer science, which is often very hard to solve, but they were able to solve it. And they had a massive supercomputer attack the problem, and they had a proof. But the proof itself, the proof certificate, was extremely long. In fact, when they did this in 2014, their proof held the record for the longest proof that appeared in a mathematical publication. So this proof certificate actually was 13 gigabytes in size. So it was reported in the media that world's longest proof is bigger than Wikipedia. That was the unit that they used. It's no longer the world's largest proof for 2 reasons. One is because they managed to simplify it later. Now the proof is only 850 megabytes long. But the other is that there was a separate proof of something else in 2016, which is 200 terabytes in size. Yeah, so there's some very big proofs out there right now. Anyway, so they were the first to show that after a certain point, after 1161, the discrepancy must be at least 3. Okay. And if you're interested, this is the sequence of 1160 signs, which is of discrepancy 2. You can check if you like that it is a discrepancy 2. All right. Okay. So now we go to 4. Okay. So we now know that if you go long enough, after 1,161 steps, the discrepancy must be at least 3. When does the discrepancy hit 4? Does it ever hit 4? Okay. So the same scientists, Konev and Lisitsa, were able to construct a sequence which is fairly long. They found a sequence of length 13,900. I'm not going to show it to you here. But there's a very, very long sequence where the discrepancy always stays at 3. It never goes to 4. But they didn't know if that was the longest one. That was just the longest one I could find. And you'd have to solve a 4-sat problem. I don't think any computer actually could settle the question of what's the longest sequence that would have discrepancy 3. For which you have to have discrepancy 3. That's too hard for today's computers. And in fact, it was not known until 2015. It was not known whether you had to reach 4. It could be that maybe 3 is the most you have to get. Maybe sequences could go on forever for discrepancy 3. So what I did in 2015 was I actually showed that the discrepancy does actually have to grow. That as you go further and further out to the integers, the discrepancies must become unbounded. Okay, so eventually, for n big enough, the discrepancy must become 4, must become 5, and so forth. I didn't say when it would happen. It's sort of a non-constructive, well, it is constructive, but the bounds are very, very bad when it happens, but I can prove it does happen. And the funny thing is that this, the statement is very combinatorial. The argument, the Sudoku type argument, this is, combinatorialists recognize this as combinatorics. But the proof actually used tools from all over mathematics. We used tools from number theory, probability theory, and even information theory. So to try to understand what's going on. So when you try to solve a problem like this, you want to know sort of what the enemy is. Like there are so many different sign sequences in the world. which ones are the ones that will cause the most trouble? Which ones are the sequences whose discrepancy is very small, which would be almost counterexamples to the theorem? Okay, so how can you make this discrepancy really, really small? Okay, so as I said, you could try using a random sequence. Sorry. You can try. You can try. Sorry. I'm having a slight problem with this microphone. Yeah. So if you try random, I'm sorry. I'm going to. So is there someone who can help me with this microphone? Yeah. Or if I can turn. Okay, actually, I think I will use this microphone instead. Oh, Thank you. Thank you. Sorry about that. Okay. All right. If you pick a random sequence, then the discrepancy is about square root of n. But as before, random sequences are actually not the best sequences. They're not the worst sequences usually. So a good example of a sequence which is not random and actually would have a good chance is a possible candidate or counterexample. So the best examples actually come from number theory. And so one example of a sequence which shows up is what's called the Liouville function. The Liouville function lambda is a function which is plus 1 or minus 1. It's defined to be plus 1 when n is the product of an even number of primes, and minus 1 when you're an odd number of primes. So, for example, lambda of 4 and 6 is plus 1 because 4 is 2 times 2, 6 is 2 times 3, even number of primes. Whereas lambda of 5, lambda 30, which is 2 times 3 times 5, is minus 1. So maybe if I go back to this, to this picture here, if I draw you lambda of n, looks like this. Okay, so odd number of primes, even number of primes, odd, even, odd, even, and even, odd, odd. Okay, so that's what the Liouville function, the Liouville function looks like. So the importance of this function, the relevance of this function, I guess I didn't write it here, so maybe I'll use this notebook here, is that it has a property of being completely multiplicative. Okay, that it has the following special property, that if you take a Liouville function of a product n times m, then it factors into the product of lambda of n and lambda of m. For example, lambda of 9 is the product of lambda of 3 and lambda of 3. So plus 1 is minus 1 times minus 1. That's important because that means that you can factor these sums. Okay, so if you're looking at a progression, if you're looking at a progression here, you can actually factor this. Okay, like that. So when you take a multiplicative function and you sum it on a homogeneous progression like this, then you can pull out this factor, which is just plus or minus 1, and you just get a partial sum. So asking for whether these discrepancies are bounded or not is the same as asking whether the partial sums are bounded or not. And so it's a simpler question. And so if you want to know whether the Liouville function is a counterexample to the Irish discrepancy problem or not, you need to know whether the partial sums of the Liouville function are bounded or unbounded. So this turns out to be a very well-studied problem. It turns out that these partial sums are connected to a very important object in number theory called the Riemann zeta function, and to a very famous hypothesis, the Riemann hypothesis about the zeros of the zeta function. There's actually a formula that connects this sum to the zeros and to where the zeros are. So, for example, if the Riemann hypothesis is true, then that implies actually that these partial sums never get more than size square root k or so. That the size of these sums turns out to be about square root of k times log k, but essentially square root of k. Now, we can't prove that. We don't know the Riemann hypothesis. But we do know there's at least one zero. So the Riemann hypothesis says that all the zeros of the zeta function, all the non-trivial zeros, lie on a certain line. And we don't know that, but we do know at least one of them lies on the line. In fact, even the first trillion zeros are known to lie on this line. And just knowing one zero there, actually that implies a lower bound. You can use that to show that this sum is of size at least root k infinitely often. Okay. And in fact, this connection to the Riemann hypothesis, this is the reason why Erdős was interested in posing this question. He was hoping that it would help people use tools from combinatorics to attack these sort of number theory questions. Although, as it turned out, it didn't work out that way. The proof works in reverse. We use number theory methods to solve the problem, and so we don't actually get any new number theory out of this the argument. But still, okay. So here, by the way, these are the partial sums of the Liouville function. So if you sum, say, the first 10,000 elements of the Liouville function, you get like minus 100 or so, and it does grow a bit like square root of k if you compare. And all these oscillations have to do with zeros of the zeta function, which is a great story, but no time to talk about it here. Okay, so that sequence is not very low discrepancy. So there's another sequence which is low discrepancy, which is somewhat a more dangerous counterexample. Also comes from number theory, and they're called Dirichlet characters. So Dirichlet characters are like the Liouville function in that they are also completely multiplicative, but they are also periodic. So rather than give you the full definition, just give you an example. An example is called chi3. This is a Dirichlet character which is +1 when you have a remainder of 1 mod 3, -1 when you're 2 mod 3, and 0 when you're 0 mod 3. So actually the easiest way to show you this function is just to just draw the table again. So going back over here. +1, -1, 0, +1, -1, 0, +1, -1, 0. Okay. So that's chi3. Okay. It's a shame I can't put, anyway. So as it turns out, this function, the partial sums of this function stay bounded they never get bigger than 1, in fact. So if you look at the sequence, if you sum the first 2 or first 3 or first 4 elements of the sequence, it's always either 1 or 0. 1, 0, 0, 1, 0, 0. It's either 1 or 0. And it's multiplicative, so the discrepancy of the sequence is 1. This is a bounded discrepancy sequence. But it's not a counterexample to the discrepancy problem because it got zeros in it, right? You're not allowed to use zeros. That's cheating. If you allow to use zeros, you can just say 0, 0, 0, 0, 0. Right? That is a sequence of bounded discrepancy. Right? But it's non-zero 2/3 of the time. So in some sense, it's 2/3 of a counterexample. Right? So it doesn't solve the problem, but it does show that somehow the discrepancy problem is actually very close to being false. That there are sequences that are, say, 2/3 plus or minus 1s that have bounded discrepancy. And there are variants of the sequence that you can make say 6/7 of the elements non-zero or 99% of the elements non-zero and still have bounded discrepancy. You can get very close to counterexamples to this problem. Right. And in fact, so it is. There are some zeros in it. It is possible to modify the example a little bit. Maybe I'll skip this slide. But if you replace the zeros with plus or minus ones, you can make a sequence of plus or minus ones whose discrepancy is not bounded, but it grows very slowly. It grows logarithmically. So there is a sequence which is like a Dirichlet character. You modify it a little bit. You change the zeros to plus or minus ones in the right way, and you can make this sequence the discrepancy grow only like log n. So it goes very slowly, which helps explain. Which is consistent with what we see. It took 12 elements to get discrepancy 2. It takes 1,161 elements to get discrepancy 3. It takes at least 13,000 to get discrepancy 4. That smells like logarithmic growth. So what these examples tell you is that, first of all, multiplicative sequences are maybe the most dangerous sequences. And within the multiplicative sequences, the Dirichlet characters and things like Dirichlet characters are the most troublesome sequences, the most likely candidates for counterexamples. That's sort of what these examples tell you. So back in 2010, actually, this problem was attacked by what's called a Polymath Project, which is a fairly new way of doing mathematics. So traditionally, mathematicians, we sit alone, or maybe we work in groups of 2 or 3, and we don't share what we do until we've finished our problem. But about 10 years ago, Timothy Gowers, who's another Fields medalist, proposed a different way of doing mathematics, sort of crowdsourced mathematics, where you make a project and you open it up to anyone can participate online, usually participate on, say, a blog or some other discussion forum on a single problem, and everyone contributes a little piece to the argument, and it's all open. So, even if you have a silly idea, you put it on the blog, and maybe other people say, yes, that's a good idea, or no, that doesn't work because of this, and so you crowdsource the progress. So it's a very different way of doing mathematics. Sometimes it works, sometimes it doesn't work. And so there's about 14 of these projects so far. And this was the fifth. So the fifth project was to attack the Erdős discrepancy problem. So Polymath 5. So they worked for about 2 years. I participated a little bit in that, actually. They didn't completely solve the problem, but they made some progress. They simplified the problem. One of their achievements was that the actual achievement is actually more complicated, but roughly speaking, they explained why multiplicative functions were the most dangerous type of sequence. So very roughly speaking, they were able to show that if you could prove that completely multiplicative sequences had unbounded discrepancy, that would imply that all sequences have unbounded discrepancy. So if you wanted to prove to settle the Erdős discrepancy problem, you really just had to understand multiplicative sequences. I don't have time to say why. The argument uses a variant of Fourier analysis that you can use something like a Fourier transform to decompose any sequence into multiplicative sequences, roughly speaking. Okay. But anyway, but they managed to reduce the problem to multiplicative sequences, which is a big simplification. And so now the simplified problem is if you have a sequence which is completely multiplicative, such as the Liouville function, or maybe something like a Dirichlet character, are the partial sums of these functions unbounded? So this is a simpler problem, and if you can solve this, you can basically solve the full problem. I'm lying in a way which is kind of technical, but this is essentially what they did. So that's one thing they did. Another thing they did was that you can divide multiplicative functions into two classes. There are those that look like Dirichlet characters and those that don't look like Dirichlet characters. And there's a way to measure distance to a Dirichlet character to make that precise. It's kind of like the distinction between rational and irrational numbers. And they were able to show that if your multiplicative function looked like a Dirichlet character, then the discrepancy did grow. It grew very slowly, but it did grow. So they were able to handle sequences that behaved like Dirichlet characters, the most dangerous case. But all the other cases, sort of like the irrational multiplicative sequences that did not behave like Dirichlet characters, like the Liouville function, this they could not handle. And so they tried for 2 years and they got stuck and gave up. In retrospect, there's a good reason they got stuck, because they needed a breakthrough in number theory that only happened in 2015, and they gave up in 2012. Sometimes sometimes it's not ready. Sometimes you attack questions before their time. So really, so a typical sequence that you need to study is the Liouville function. So really, the model question really is: are the partial sums of the Liouville function unbounded? Now, we already know this to be true, as I said, because we know about the zeta function. So the Liouville function is connected to the zeta function, and because of what we already know about zeta functions, we can prove this, but that's a very special connection. Only the Liouville function is connected to the Riemann zeta function. Any other multiplicative function has no connection. So you'd like a different way to make these sums unbounded. Okay. So you somehow want to show that these, the Liouville function, the signs, fluctuate about as much. You like them to fluctuate like random sequences, because random sums do fluctuate. They become unbounded. So you would like some to show some sort of randomness in the in this sequence. Okay, so there are some ways to show that. You can use some fairly elementary arguments to show some sort of random behavior in the Liouville function. So if you have a random sequence, every so often you would expect, in fact half the time, you would expect consecutive pairs of a random sequence to have the same sign. Like if you have a +1 somewhere, the next element, half the time you expect +1 as well. So you would expect adjacent elements to be of the Liouville function to be equal about half the time. Okay, so for example, going back to my little table here. Oops. All right, so with the Liouville function, you can see there's lots of pairs. There's lots of pairs of elements where the sign is the same. I'm sorry, I should make that. Okay. So for example, at 11 and 12, adjacent numbers have the same sign. This happens about half the time. And it's easy to prove that actually they do fluctuate at least a fair fraction of the time. So let me see if I can give you another proof here. Okay, so I can tell you that lambda of n equals lambda of n plus 1 infinitely often. Okay, so again we suppose, so here's the last proof I'll give. Yep, suppose not. Okay, so what that means is suppose the sign keeps changing. Okay, so suppose that suppose that for all n big enough, okay, for large n. Okay. Now you can do another Sudoku type thing. So a slightly more complicated Sudoku type calculation. So suppose, for example, lambda of n is +1, and then it changes sign. It's -1. Okay. But if lambda of n is say +1, then lambda of 2n, because it's multiplicative, and lambda of 2 is -1, lambda of 2n has to be -1. Okay, lambda of 2n has to be the negative of lambda of +1, and because lambda of n plus 1 is -1, lambda of 2n plus 2 is +1. Okay? All right. But what about lambda of 2n plus 1, which is in the middle between 2n and 2n plus 1, 2n plus 2? So it could be either +1 or -1, but no matter which sign it is, you will create an adjacent pair with the same sign. So if lambda 2n plus 1 is equal to -1, then these two adjacent elements would have the same sign, and if it's equal to +1, these two elements will have the same sign. So no matter what you do, you have to create elements of the same sign. And in fact, this argument shows you, in fact, that if you work it through, that about at least 1/3 of the time, adjacent elements must have the same sign. That's what this argument proves for you. Oops. Sorry. Okay. Not quite yet. All right. So, so that was a fairly simple argument that showed that you must have you must have pairs of the same sign quite often. In fact, 1/3 of the time. So you could think maybe about the opposite problem. Can you have pairs that are opposite sign infinitely often? And that sounds like almost the same question, but that's a lot harder, as it turns out. And so the question of asking whether opposite signs happen. So you would expect this, because if you want random behavior, you want equal signs half the time and opposite signs half the time. But but it wasn't until 2015 until it was actually known that opposite sign fluctuations happen a positive fraction of the time. And this was actually a big breakthrough in number theory by two number theorists, Matemática and Radzivil, who used really cutting-edge analytic number theory, lots of Dirichlet series. There's no time to, and it's a bit too advanced to present here. But using some high-powered number theory, they were able to show this sort of pattern also occurred infinitely often. So this is sort of moving towards showing that the Liouville function behaves like a random sign sequence, and random sign sequences should have unbounded sums. Okay, so it turns out that there are more complicated arguments, it's like really expert level Sudoku puzzles in some sense, that show that these you need these sort of results to show unbounded sums. That if the partial sums of the Liouville function stayed bounded, you could run an argument like this, and you could eventually show that this would lead to some very strong irregularities, some very strong biases or non-random behavior in the Liouville function. Now, what do I mean by non-random behavior? For example, maybe that this sort of pattern occurs way too often or way less than what you expect. That there's a certain expectation of how often these things should happen, but there's a bias that this either happens too much or too rarely. It's actually more complicated than that. The type of bias that shows up also depends on residue classes of n. So a type of bias that might cause partial sums to be bounded is that maybe adjacent sign patterns occur very often for numbers at n that are 7 mod 10, but they don't occur very often for numbers that are 3 mod 10. So that's a more complicated example of a bias. But you can prove that these sort of biases are the only sort of biases that could cause these partial sums to stay bounded. Now, to actually prove that is not easy, and you actually have to use tools from information theory, in particular to even measure what bias means. You can think of lambda of n as a string of digits, binary digits, and you can talk about the information content of that string. And you can ask about how much of the information content of that string connects with things like the last digit of the element of the number n in your sequence. And there's a way of measuring mutual information between these sort of statistics. And so that turns out to be the right concept to use, as it turns out. But anyway, you can prove that partial sums are unbounded unless there is some strong bias, some strong mutual information between the Liouville function as a string of bits, of signs, and things like the residue class mod 10 or mod 17 or mod some other base. And I was not able to exclude any one of these. So it is possible that maybe the Liouville function has some strong bias or shared information with the natural numbers modulo some base, like mod 10 or mod 17 or mod whatever. So I wasn't able to show any given base that there was that it was unbiased. But using more information theory, something called the Shannon entropy inequalities, I was able to show that you couldn't have bias with too many things at the same time. So it's like, people can be biased in one way or another, but you sort of kind of too many biases. That if you are very strongly biased with regards to n mod 5, then you can't also be strongly biased with n mod 7 and n mod 11. There is some independence between all these different variables, which causes at least some of these residue classes have to be unbiased. And so there was a trick. You have to use the pigeonhole principle to find some good residue classes where there is no bias or very little bias. And for those residue classes, then you can say that the sequence behaves enough like a random sequence that you can use tools from probability theory. And there's a specific tool I use called Hoeffding's inequality, which you can use to show that the partial sums just barely grow unbounded. And well, okay, so it's very technical, unfortunately, how that actually works. But eventually, what that does for you is it just says that any multiplicative function, like the Liouville function, which is not a Dirichlet type sequence, has unbounded discrepancy. Polymath already showed that all the Dirichlet sequences have unbounded discrepancy. And once you can do the multiplicative sequences, you can do all the sequences. So you put everything together, and that actually solves the whole problem. But I think I will stop there. So thank you for listening.
Are there any questions or comments? You can raise your hand.
In English, I suppose.
Yeah. Por favor. Yeah.
So for the problem you tackled, the sequences were of -1 and +1. So I mean, is there anything that can be said about sequences that have more symbols? Like, I think that maybe that bounded numbers, like other than +1 or -1.
Right. So the question is, can you say anything if your sequence is not just +1 or -1, but other numbers? So it turns out that the argument also works for complex numbers. So you have a sequence of complex numbers of size 1. So maybe +1, -1, also I, minus I. That also works. In fact, you can take vectors in any vector space, any Hilbert space of magnitude 1, or even magnitude bigger than 1. And there's actually a similar result. The same method actually works. But the original question of Erdős was just +1 or -1.
I remember when you talked about the Riemann zeta function.
Yes.
I wanted to know if the proof that was using the Riemann zeta function was at least like simpler than your proof to this problem.
Yeah. So
I know that the Riemann zeta function is not proof, the Riemann hypothesis like that, but
right. Yeah. So the if you use the zeta function to prove that the Liouville sums are unbounded, all you need to prove is that there is 1 0 on the critical line, and that you can prove by computer. You can just numerically plot the zeta function, and you just see that there's a 0 there. You can also prove that there's infinitely many zeros on the critical line. That was known for a long time. So the proof I use, so there's this number theory result of Matamaki and Ratziwell that ends up being used in the proof, in my proof. And they also use some very non-trivial properties of the zeta function. Not exactly the same properties, but something called a zero-free region. There's a large region where there are no zeros. There's known to be no zeros. So because of that, actually, we don't learn anything new about the zeta function from this proof, because we use very powerful methods to prove something very, very weak, actually, about the zeta function, unfortunately. So, okay. So, this wasn't, as it turned out, this wasn't the way to prove the Riemann hypothesis. Anyway.
Hello. Here. I want to know about those Polymath project.
Yes.
My question is, how do you choose the problem to tackle?
Right. So the way it works is that we have a forum, a blog, where people can propose Polymath projects. And so they state the problem, they argue the motivation, and they argue why it might be a good problem for Polymath. So not every problem is a good Polymath project. So I would not propose the Riemann hypothesis, for example, as a Polymath project. You want a project which is can be broken up into smaller parts, and people with different expertise can work on different parts. And a question which is not too technical, so many people can understand it. So you don't need a lot of background. So like for this Polymath project, there were people who were working on it who were not professional mathematicians, but they were good programmers. They supplied, and they happened to have a supercomputer or something. Some of them were actually just very good with puzzles. There were some people. So there were some very good Sudoku players actually who were contributing to that project. And just finding sequences. And so a good project, you want a project that can benefit from many different types of participants. And if there's enough interest, then we formally launch the project and we see how it goes. Sometimes we make a proposition and only 2 or 3 people are interested, and then we don't start a project because there's not enough interest.
I have a question. When you are, for example, using a Monte Carlo approximation and you are measuring discrepancy in order to have a clue of how good your approximation will be, then you start increasing the dimensionality of the problem, and you know that in general you're going to have troubles finding good samples because you're not going to hit the typical set of the distribution.
Yes.
So when the problem gets more complicated, let's say you have 2 main problems there. Is the one the dimensionality and then the discrepancy. Do you have a clue of what is heavier than, which one is heavier than the other in as far as you are increasing the dimensionality?
Right. So the question, if I understand it, is what is the role of discrepancy theory as the dimension gets larger? So I gave an example in 2 dimensions. These low discrepancy sequences work very well, and as long as the dimension is low, 3, 4, 5, these sort of methods work well. Yeah, because nowadays a lot of big data is very high dimensional, and the classical low discrepancy sequences actually do not work very well in high dimensions. So actually other techniques are used to explore very high dimensional spaces. So there's these Monte Carlo methods, what's it called? Monte Carlo Markov chain type methods and Metropolis algorithm. There are more modern methods to treat high dimensional data, which is quite different actually. So what I was discussing is also more classical discrepancy theory from like 100 years ago, which was more interested in computing volumes and areas of low dimensional objects. Yes, but it's true. High dimension is a very different game. And of course my problem is one dimensional. It's almost a completely different field how to sample accurately high dimensional spaces, and that's a very important modern topic in say probability theory or statistics. But it's not actually. It's quite different from what I discussed here.